Hi, we are looking at Chapter 10, Section 8, Geometric Probability. There's going to be two basic situations that we're going to look at in this section. One is where we take our situation and we break it down into a line segment, perhaps length of time, something like that. And then what we're going to do is we're going to try to see what are the chances that we land on a particular area on our line segment. So the probability of that happening is merely the length of segment AC divided by the length of segment AB. Our desired location out of all possible locations. In the second situation, what's going to happen is we are going to look at probability in terms of areas. So if we were to randomly choose a point that we know is going to land inside of this polygon, what's the probability that it lands in region 2? Well, once again, our desired location is the area of region 2. All possible locations are the area of region 1, and region 1 again is just this giant polygon. Okay, both of those concepts, whether it's the line segment length or the area, is using the concept of part out of the whole, or, as I've been saying, desired result out of all possible results. Basic probability, for example, a drawer has 10 socks, 7 are red. You reach in and there's that important word, randomly choose a sock. What is the probability of drawing a red sock? Well, the desired feature, red, there are 7 of those, out of all possible socks, 10. And so the probability of drawing a red sock is 7 out of 10. Okay? Second example, there are 10 blue marbles total, 6 green, 2 blue and 1 red in a bag. I guess that would make 12 blue, and that's okay. You reach into the bag and you randomly choose a marble. What's the probability of choosing a red marble? Well, there's only 1 red desired outcome in the bag. If you add together these other marbles, 16, 17, 18, there are 19 total marbles. So then the question asks, what's the probability of choosing a blue or a red marble? Well, you're still choosing out of the 19, but a blue marble would be, because of my weird problem, 12 out of 19, plus there's a chance that you could choose that 1 red, 1 out of 19, which gives you a grand total possibility of 13 out of 19. Now, with probability, unlike other fractions that we'll create, you do not have to reduce. I'll make a note of that. Do not have to reduce probability fractions. Whoops, off the page. Don't have to reduce probability fractions, and that might be important to you as we proceed. Okay, we're going to go on to page 2 and the examples on that page. Okay, for the example 2, or examples on page 2, pardon me, the first one says, a random point K is to be chosen on segment AF. Okay, so we know we're landing on this segment. What's the probability that K is on segment CF? So our desired location is right here in CF. Now, if we also take a look, we can see that this segment AF has been partitioned off into equal pieces. And that's important to us. I don't know what length those pieces are. I just know they're equal. And there are, if you take a look and count, there are 1, 2, 3, 4, 5 of those pieces. So, as far as our desired location is anywhere from C to F, that's 1, 2, 3 units is our possibility out of 5. So the probability that K lands on segment CF is 3 out of 5. Okay, and the second example, it's a carnival table. The area is 1.5 square meters. I think we've all seen this. The table's laid out. And then on top of the table are laid plates. So you usually end up with something like this, with little plates on top of it. And there's space between the plates, etc. So what happens here is the table itself is 1.5 square meters. The total area covered with plates is only 1 square meter. And there's no overlap of the plates. So what's the probability that a tossed nickel lands on a plate? Okay, and again, we're assuming that the nickel will land on the table. It's not going to fly off. So with that in mind, our desired location is a plate, and the plates take up 1 square meter. Our total possible area, 1.5. Now, for fractions and for probability, we don't want to leave a decimal mixed in with a fraction. So you have some options of how you can achieve integers for the top and for the bottom. The easiest one to do is to multiply the top and the bottom by 2, and when you do that, you will end up with a probability of 2 over 3. So there's a 2/3 chance that when you toss the nickel, you land on the plate. Okay, in the next example, take a second, stop the video, read the information, and see what you come up with. Okay, hopefully you thought about this, and what it's telling you is you have your segment AF, and it's been broken into 1, 2, 3 equal pieces. Now, that being said, you're also told each of these little guys in between here is equal to each other, which means there are 1, 2, 3 individual segments in that zone. Well, if that's the case and the 3 pieces are all equal, there should be 3 segments in the first zone and 3 individual segments in the last zone. They're just not drawn for you. So we want the probability, okay, K is going to land on AF. What's the probability it will land on segment BC? Well, segment BC is right here, and segment BC is merely 1 unit out of the 9 possible units that are on that segment. Okay, the next question asks you, what's the probability that this random point lands on segment CF? So we take a look, and segment CF is 3 plus 2 more. Segment CF is 5 units long, again, out of the 9 possible units. Okay, take a second, read the situation for example 4 and see what you come up with. Okay, in example 4, it gets interesting because in example 4 what happens is we're looking at time taking place, but we can break that time up into the lengths of segments. So what happens here is a new train arrives at a station every 20 minutes. Each train stops at the station for 3 minutes, and then of course it leaves. So what we're looking at here is a 20-minute window. Whoops, 20 whole minutes from train arrives to the next train arrives. In that time frame, once the train arrives, it sits there for another 3 minutes. So go ahead and make your mark. And that train sits there for 3 minutes, and then it leaves. Okay? So when that train leaves, you now have 17 minutes that there's no train sitting there. Okay, so Hopefully you're okay with that scenario. If you have any questions, of course, ask about them in class. So you come running into the station and you run down the stairs. What's the probability of you boarding the train immediately? Well, in this cycle of arriving and the next one arriving, if you come down and you're going to catch a train immediately, that means you must have come downstairs in this first section, the 3 minutes when the train is sitting there. So 3 is your desired location, and the total is a 20-minute cycle. So 3 out of 20 is your probability of boarding the train immediately. Okay, so the next problem is a little different. You come downstairs now, and there's no train there. What's the probability of you waiting less than 10 minutes? So if we think about that, if we came downstairs when there's no train, that means we must be in this 17-minute spell when the train is not there. So our total possible is 17. Now, what's the probability of you waiting less than 10 minutes? Well, less than 10 minutes would be someplace over here for less than 10 minutes. And so the chances of that happening is 10 out of 17. Again, less than 10 minutes includes everything up to 9 minutes, 59 seconds, and 99 1/millionths of a second, so it's taking into account everything up to 10. So 10 out of 17 is the probability that when no train is there, when you're in the orange zone, that you'll end up waiting less than 10 minutes for the train. Okay, we're going to pause here, and we're actually going to stop here, and we will complete the rest of these examples in class. Actually, I'd like for you to do example E. So let's make a note of that. Do example E and example F on your own. I'll check them in class, and then we'll continue with the rest of the examples. Stay classy.